Have you ever wondered what the universe looked like in its earliest moments? Picture this light that has traveled across the vast expanse of space for over 13 billion years, carrying whispers from the dawn of time itself. This isn't just any light, it's the cosmic microwave background, the oldest light in the universe, a faint glow that fills every corner of the cosmos like an echo from the Big Bang. Think of it as a cosmic fossil, a snapshot of the universe when it was just a newborn, hot and dense, barely 380,000 years old. And here's the mind-blowing part: this ancient light is still all around us, invisible to our eyes but detectable with the right instruments, holding secrets about how everything we know began. What if I told you that this relic of the early universe isn't just a static backdrop? It's a treasure trove of information, a cosmic puzzle waiting to be decoded. Tiny fluctuations in this light, patterns no bigger than 1 part in 100,000, reveal the seeds of galaxies, the blueprint for the vast cosmic web we see today. Scientists have spent decades studying these faint ripples, peeling back the layers of time to understand how the universe evolved from a searing hot plasma to the sprawling tapestry of stars and galaxies we inhabit now. The cosmic microwave background isn't just a remnant of the past, it's a key to unlocking some of the biggest mysteries in science, like what happened in the first fractions of a second after the Big Bang, or why the universe is expanding at an ever-increasing rate. And that's exactly what we're diving into today. Over the next 30 facts, we'll unravel the story of this ancient light, from its accidental discovery to the groundbreaking insights it's given us about the cosmos. You'll learn how it's mapped with astonishing precision, why it's colder than the deepest reaches of space, and what it tells us about the fate of the universe itself. So get ready to travel back in time to an era before stars, before planets, even before atoms as we know them existed. Because the cosmic microwave background isn't just a glimpse into the past, it's a window into the very fabric of reality. Let's begin. Here's the first astonishing fact about the cosmic microwave background. It's literally the afterglow of the Big Bang, a fading whisper of light from the universe's fiery birth. Picture the universe just 380,000 years old, a swirling sea of unimaginably hot plasma so dense that light couldn't travel more than a tiny distance before being absorbed. Then, in a cosmic instant, everything changed. As the universe expanded and cooled, protons and electrons finally combined to form neutral atoms, clearing the fog and allowing light to stream freely for the first time. That light stretched and dimmed over 13.8 billion years of cosmic expansion, is what we now detect as the cosmic microwave background. But here's where the story gets even more fascinating. This relic radiation wasn't discovered by some grand, deliberate search. It was stumbled upon almost by accident. In 1965, 2 radio astronomers, Arno Penzias and Robert Wilson, were troubleshooting a strange, persistent hiss in their antenna at Bell Labs in New Jersey. No matter how they adjusted the equipment or cleaned out pigeons nesting in the horn-shaped receiver, the noise wouldn't go away. It was everywhere, equally intense in every direction, like a faint hum permeating the cosmos. At first, they thought it was just interference, maybe some earthly signal or a defect in their setup. But when they consulted physicists at Princeton, they learned the truth. They'd accidentally detected the oldest light in the universe. This discovery was monumental because it settled one of the biggest debates in cosmology. At the time, some scientists still argued whether the universe had a beginning at all, or if it had simply existed forever in a steady state. The cosmic microwave background shattered that idea. Here was direct evidence of a hot, dense past, proof that the universe had indeed expanded from an explosive origin. Penzias and Wilson's work earned them a Nobel Prize, but more importantly, it gave humanity its first concrete glimpse into the universe's infancy. What's truly remarkable is how perfectly this ancient light matches predictions made years earlier. Theorists like George Gamow had calculated that if the Big Bang happened, the universe should be filled with cooled radiation at a temperature just a few degrees above absolute zero. And sure enough, when Penzias and Wilson measured their mysterious signal, it lined up almost exactly around 2.7 Kelvin, or roughly negative 454 degrees Fahrenheit. That's colder than the deepest void of space today, but it's exactly what you'd expect from a universe that's been stretching and cooling for billions of years. So the next time you look up at the night sky, remember this: you're not just seeing stars and galaxies, you're witnessing a universe still echoing with its own creation, a place where even empty space glows faintly with the light of its origins. And all of that, the vast cosmic web, the swirling galaxies, even our own existence, traces back to that primordial flash now frozen in microwaves, waiting for us to decode its secrets. That faint glow filling the cosmos isn't just localized to one corner of space, it's everywhere. No matter where you point a telescope, the cosmic microwave background is there, a silent witness to the universe's fiery infancy. What makes this so astonishing is the sheer uniformity of it. From the depths of intergalactic space to the void between stars, this ancient light maintains an almost identical temperature of 2.7 Kelvin, just a hair above absolute zero. That's negative 454 degrees Fahrenheit, a chill so profound it defies earthly comparison. This uniformity tells us something extraordinary about the early universe. When light first broke free during that moment of recombination, 380,000 years after the Big Bang, the cosmos was remarkably smooth. Matter was distributed with near-perfect symmetry, creating a sea of plasma so evenly heated that its glow today varies by less than 1 part in 100,000. Imagine baking a cake where every single crumb is identical down to the microscopic level. That's the level of consistency we're talking about. But here's the twist: those tiny variations we do detect are where the magic happens. Those minuscule fluctuations in temperature, some spots slightly warmer, others fractionally cooler, were the gravitational seeds for everything we see today. They're the universe's original blueprints, the subtle wrinkles that eventually grew into galaxies, clusters, and the vast cosmic web. Without them, the cosmos would have remained a featureless soup of particles, never giving rise to stars, planets, or us. Scientists measure this uniformity using instruments like the Planck satellite, which mapped the CMB with such precision it could detect temperature differences as small as 1/1,000,000th of a degree. What they found was a snapshot of the universe at its most pristine, a time before gravity had sculpted the chaos into structure. The fact that this light reaches us from all directions also confirms something profound. The Big Bang wasn't an explosion in space, but an expansion of space itself, stretching that primordial glow into the faint microwave hum we detect now. So when you hear that the CMB is everywhere, it's not just a poetic notion, it's literal. This light has traveled uninterrupted for nearly 14 billion years, a relic so pervasive that even the emptiest patches of space still hum with its presence. And buried within that glow are answers to questions we're only beginning to ask about how the universe began, how it grew, and where it might be headed next. That seemingly perfect uniformity of the cosmic microwave background hides a fascinating imperfection, one that holds the key to everything we see in the universe today. Zoom in close enough and you'll discover the CMB isn't flawlessly smooth. Instead, it's speckled with microscopic temperature variations, patches slightly warmer or cooler than their surroundings by just a few millionths of a degree. These tiny fluctuations, called anisotropies, might sound insignificant, but they're cosmic gold. They're the gravitational fingerprints of the early universe, the primordial bumps and wrinkles that would eventually grow into galaxies, clusters, and the vast cosmic web. The first solid evidence of these anisotropies came in 1992, when NASA Cosmic Background Explorer Satellite, or COBE, delivered a revelation. After years of analyzing the CMB's faint signal, CMB instruments detected those subtle temperature differences, proof that the early universe wasn't perfectly uniform after all. Imagine seeing a seemingly blank canvas suddenly reveal faint brushstrokes under a magnifying glass. That's what CMB did for cosmology. Its findings confirmed a critical prediction. Without these initial density variations, gravity would have had nothing to work with, and the universe would have remained a featureless expanse forever. But CMB was just the beginning. The European Space Agency's Planck satellite, launched in 2009, took this investigation to staggering new heights. With sensitivity 100 times greater than CMB, Planck mapped the CMB in exquisitely fine detail, measuring temperature variations as small as 1 part in 100,000. What it revealed was a cosmic tapestry of hot and cold spots, some no larger than 1/10 of a degree across the sky. These patterns weren't random. They matched precisely what physicists expected from sound waves rippling through the early universe's plasma, frozen in time when light first broke free. Here's why these anisotropies matter so much. Those slightly denser regions, the warmer spots in the CMB, acted like gravitational anchors. Over billions of years, they pulled in surrounding matter, growing denser and hotter until they collapsed into the first stars and galaxies. The cooler spots, by contrast, marked the voids between these structures. In essence, the entire architecture of our universe was encoded in those faint temperature differences, a blueprint written in microwaves. What's truly mind-bending is the scale of this process. Those initial fluctuations were unimaginably small, less than 1% variations in density. Yet from such modest beginnings, gravity sculpted everything from dwarf galaxies to colossal superclusters. It's like watching a single snowflake trigger an avalanche that reshapes a mountain range. And thanks to missions like CMB and Planck, we can now trace that avalanche back to its first moments, seeing the universe not as it is today, but as it was before the first star ever ignited. So when you hear that the CMB isn't perfectly smooth, remember, it's those imperfections that made us possible. Without them, the cosmos would be a vast, empty sea of darkness. Instead, we live in a universe rich with structure, where every galaxy, every planet, and every atom in our bodies owes its existence to those faint whispers of imbalance from the dawn of time. The cosmic microwave background isn't just ancient, it's also the coldest natural phenomenon in the universe, lingering at a frigid 2.7 degrees above absolute zero. To put that into perspective, even the deepest voids of intergalactic space, where temperatures plummet to around 3 Kelvin, are slightly warmer than this primordial glow. Absolute zero, the theoretical temperature where all molecular motion stops, sits at 0 Kelvin, or negative 473 degrees Fahrenheit. The CMB hovers just a whisper above that, colder than the Boomerang Nebula, a cosmic ghost 5,000 light-years away that was once considered the coldest known place in nature at 1 Kelvin. What's wild is how this temperature reveals the universe's relentless expansion. When the CMB first emerged, it was blazing hot around 3,000 Kelvin, as scorching as the surface of a red giant star. But over 13.8 billion years, space itself stretched, redshifting that light into longer, lower-energy microwaves and draining its heat. It's like taking a piping hot cup of coffee and leaving it in the freezer for billions of years until it's colder than the void between galaxies. But here's the kicker. Even this unimaginable chill isn't perfectly uniform. The CMB's temperature dips and rises by microscopic amounts across the sky, those anisotropies we mentioned earlier. Some patches might be 2.701 Kelvin, others 2.699, variations so slight they'd be undetectable without space-based telescopes like Planck. Yet these fluctuations tell us everything about how the cosmos evolved. Warmer spots marked denser regions where galaxies would later cluster. Cooler areas became the cosmic deserts between them. Compare this to other celestial temperatures and the CMB stands alone. The sun's corona burns at millions of Kelvin, neutron stars freshly born from supernova can hit 1,000,000,000,000 degrees. Even the cold poles of Mercury rarely dip below 95 Kelvin. Yet the CMB, a relic of the universe's most energetic moment, now blankets everything in a near-absolute zero embrace. It's a paradox. The aftermath of the Big Bang, once unimaginably hot, has become the coldest thing in existence. And that's not just a curiosity, it's a clue. The CMB's temperature is a fingerprint of the universe's expansion rate, a way to measure dark energy's influence over time. If the cosmos had stretched faster, the CMB would be even colder. Slower, and it'd be warmer. That 2.7 Kelvin isn't random. It's a cosmic speedometer telling us how much the universe has ballooned since light first broke free. So when we study this ancient chill, we're not just measuring cold, we're taking the universe's pulse. Think of the cosmic microwave background as the universe's very first baby picture, a snapshot taken when the cosmos was just 380,000 years old. At that moment, the universe underwent a radical transformation known as recombination. For the first time, protons and electrons, which had been bouncing around in a searing plasma too hot for atoms to form, finally slowed down enough to combine into neutral hydrogen. It was like the fog clearing after a storm, allowing light to travel freely instead of being constantly scattered. That sudden transparency is what we're seeing in the CMB, the afterglow of that exact instant, frozen in time. This epoch of recombination wasn't just a minor milestone, it was the universe's first breath of structure. Before this moment, space was a glowing, opaque soup of charged particles, so dense that light couldn't travel more than a tiny fraction of an inch before being absorbed. But once atoms formed, light broke free, streaming outward in all directions. That light, now stretched into microwaves by the expansion of space, carries an imprint of the universe as it was before the first stars flickered on, before galaxies spiraled into existence, even before the simplest molecules took shape. It's the closest thing we have to a birth certificate for the cosmos. What makes this snapshot so extraordinary is its pristine clarity. Unlike starlight, which gets distorted by dust or bent by gravity on its way to us, the CMB has traveled virtually undisturbed for nearly 14 billion years. When we map its subtle temperature variations, we're looking directly at the density fluctuations of the early universe, the gravitational seeds that would one day grow into galaxy clusters and cosmic voids. It's like finding a perfectly preserved fossil from the Precambrian era, untouched by time, showing us the conditions that made complex life possible. Recombination also marks the moment the universe became cool enough for chemistry to begin. Before this point, temperatures were so extreme that atoms couldn't hold together. Afterward, hydrogen and helium could finally exist as stable gas. Without this critical transition, the raw materials for stars, planets, and life itself would never have formed. The CMB captures that fleeting window, a universe no longer too hot for atoms, but not yet cold enough for stars. And here's the most humbling thought. When we study this ancient light, we're not just observing the past, we're seeing the exact conditions that led to our existence. Every galaxy, every planet, every atom in our bodies traces back to those subtle ripples in the CMB. It's a reminder that the universe wasn't always this vast, dark expanse. It was once small, bright, and filled with possibilities, and this faint microwave glow is the only witness left to tell the tale. The cosmic microwave background doesn't just tell us about the universe's infancy, it's also one of the most precise clocks we have for measuring its exact age. By studying the subtle patterns in this ancient light, scientists have calculated that the universe is 13.8 billion years old, with an uncertainty of just 40 million years. To put that in perspective, that's like pinpointing a single day across the entire lifespan of a 100-year-old person. So how does this work? It all comes down to redshift and the stretching of light over cosmic time. When the CMB first broke free during recombination, it was visible light glowing at around 3000 Kelvin. similar to the warm hue of a sunset. But as space expanded over billions of years, that light stretched into longer, lower-energy microwaves, a phenomenon we call cosmological redshift. The amount of stretching tells us exactly how much the universe has expanded since that moment. It's like listening to a record played at half speed. The deeper pitch reveals how much the recording has been slowed down, but redshift alone isn't enough. To turn this into an age, cosmologists need another critical piece, Hubble's constant, which measures how fast the universe is expanding today. By combining the CMB's redshift with precise measurements of this expansion rate, they can rewind the cosmic tape back to the Big Bang. Imagine watching a balloon inflate. If you know how fast it's expanding now and how much it's already stretched, you can work backward to find out when it started. What makes the CMB so powerful is that it gives us a snapshot of the universe at a single, well-defined moment in time, like a freeze frame in a movie. Missions like Planck have mapped its fluctuations with such precision that we can trace the universe's expansion history like chapters in a book. Tiny variations in temperature and polarization reveal the density of matter and energy in the early cosmos, which in turn dictate how quickly space stretched over eons. Here's where things get even more fascinating. The CMB doesn't just confirm the universe's age, it also reveals the ingredients that shaped its expansion. Dark energy, dark matter, and ordinary matter all leave distinct fingerprints in this relic light. By analyzing these signatures, scientists can determine how much each component contributed to the universe's growth over time. It's like dissecting a cake to find out exactly how much flour, sugar, and butter went into the recipe, and the results are astonishingly consistent. Whether we measure the CMB, the motions of distant galaxies, or the brightness of exploding stars, they all point to the same age, 13.8 billion years. That harmony is a triumph of modern cosmology, a sign that we're truly piecing together the universe's story correctly. The CMB isn't just a relic of the past, it's a Rosetta Stone, helping us decode not only when the cosmos began, but how it grew into the vast, structured universe we call home today. Peering into the cosmic microwave background is like reading the universe's ingredient list, and the recipe is far stranger than anyone imagined. This ancient light doesn't just tell us about the early cosmos, it reveals what the universe is made of today. And the breakdown is astonishing: 68% dark energy, 27% dark matter, and a mere 5% ordinary matter, the stuff of stars, planets, and everything we can see or touch. That means over 95% of the universe is invisible to our eyes and undetectable by traditional telescopes. How does the CMB uncover this cosmic recipe? It all comes down to geometry. The patterns in the microwave background, those tiny temperature fluctuations, act like a cosmic ruler. The size and distribution of these hot and cold spots depend critically on the universe's shape and contents. If the cosmos were packed with more matter, those spots would appear larger. If dark energy dominated earlier, they'd look smaller. When scientists measured these patterns with missions like Planck, the math pointed to a universe where ordinary matter is just a sprinkle in a vast, unseen sea of dark components. Here's why this is revolutionary. For decades, astronomers assumed the universe was mostly made of atoms until the CMB proved otherwise, those anisotropies we see. Their spacing matches a cosmos where dark matter's gravity sculpted the first structures, while dark energy later drove expansion to accelerate. Ordinary matter was just along for the ride, clumping where dark matter's invisible scaffolding pulled it. Imagine building a city where 95% of the materials are transparent, yet their presence determines where every road and skyscraper goes. That's our universe. The implications are staggering. Dark energy's dominance explains why the cosmos isn't just expanding, it's doing so faster every second. Without it, gravity would have slowed cosmic growth over time. Instead, the CMB shows an anti-gravitational force winning, stretching space itself. As for dark matter, its fingerprints are everywhere in the CMB's gravitational lensing, subtle distortions where its mass bent the ancient light on its way to us. What's wild is how little we still know. Dark energy could be Einstein's cosmological constant, or something far weirder. Dark matter might be undiscovered particles, or evidence our gravity laws are wrong. The CMB doesn't answer these questions, but it frames them with razor-sharp precision. One thing's certain, the universe we see is just the tip of an iceberg, and the cosmic microwave background is our best map to the hidden depths below. So next time someone says we're made of stardust, remind them, we're also made of mysteries. The atoms in our bodies are cosmic afterthoughts, floating in a universe ruled by forces we've barely begun to understand. And all of that, the known and the unknown, is written in light older than time itself. The cosmic microwave background doesn't just hold clues about the universe's infancy, it carries fingerprints from its very first moments, a whisper of an event so dramatic it reshaped reality itself. According to the theory of cosmic inflation, the universe didn't just expand after the Big Bang. It underwent a mind-bending growth spurt, ballooning from smaller than an atom to the size of a grapefruit in a fraction of a trillionth of a second. This explosive stretch would have left marks on the CMB, subtle imprints that scientists have been hunting for decades. Those marks appear in the form of polarized light patterns, faint swirls hidden within the microwave glow. Imagine throwing a stone into a pond. The ripples that spread outward carry information about the splash. Inflation's splash was the violent stretching of spacetime itself, generating gravitational waves that tugged at the early universe's plasma. Those tugs left behind a specific type of polarization in the CMB called B modes, a cosmic signature as unique as a fingerprint. Finding these fingerprints hasn't been easy. In 2014, researchers working with the BICEP 2 telescope at the South Pole announced they detected these elusive B modes, sparking headlines about definitive proof of inflation. But there was a catch. Dust in our own galaxy could mimic the same signal. Further analysis with the Planck satellite confirmed the sad truth. Those swirls were likely just interstellar dust. Yet the hunt isn't over. The absence of these signals tells its own story, narrowing down possible inflation models and forcing theorists to refine their predictions. Why does this matter? Inflation solves some of the universe's biggest mysteries. It explains why the CMB is so uniform across vast distances. Regions now separated by billions of light years were once close enough to equalize their temperature. It also accounts for the universe's flat geometry and the absence of certain relics like magnetic monopoles. Without inflation, these puzzles would remain unanswered. The wildest part, if inflation happened, the universe we see may be just one bubble in an endless cosmic foam, with other bubble universes forever beyond our reach. The CMB is our best shot at glimpsing that unimaginable dawn, a window into forces so powerful they make supernova look like firecrackers. Every slight irregularity in this ancient light isn't just a curiosity, it's a relic of the universe's most violent and creative moment, a time when the fabric of reality itself was stretched beyond recognition. So while we haven't yet captured inflation's smoking gun, the search continues because buried in that microwave static might just be the answer to how everything began. The light we detect today as the cosmic microwave background didn't always hum quietly in microwave frequencies. It began its journey as a brilliant flash of high-energy radiation, blazing across the newborn universe like a cosmic supernova. When this light first broke free during recombination, it shone with the intense glow of 3000 Kelvin, radiating invisible and even ultraviolet wavelengths. But over 13.8 billion years, the relentless expansion of space stretched those light waves like taffy, transforming them into the faint microwaves we now observe. This phenomenon, known as cosmological redshift, is the universe's way of cooling its oldest light, turning what was once a searing glow into a frigid whisper. Redshift works because light behaves like a wave as space itself stretches. Those waves get pulled longer, shifting their energy lower on the electromagnetic spectrum. Imagine drawing a squiggle on a balloon and then inflating it. The lines stretch outward, their peaks and valleys spreading farther apart. That's exactly what happens to light traversing an expanding cosmos. For the CMB, this stretching has been extreme. Its original visible wavelengths, around 500 nanometers, about the size of a bacterium, have ballooned to millimeters, a million times longer, sliding them firmly into the microwave band. But redshift isn't just a cosmic curiosity, it's one of our most powerful tools for measuring the universe's expansion. The amount of stretching tells us how much space has grown since the light was emitted. By comparing the CMB's current wavelength to its original, scientists can calculate precisely how much the universe has expanded over time. It's like finding an old rubber band marked with measurements, stretch it out, and the gaps between the marks reveal exactly how much force was applied. What's truly staggering is the scale of this transformation. When the CMB's light began its journey, the universe was 1,000 times smaller than it is today. That means every wavelength of light emitted back then has been stretched 1,000-fold, draining its energy into the cold, microwave afterglow we detect now. Even more mind-bending, this process continues. As the universe keeps expanding, the CMB will redshift further, fading into longer radio wavelengths until, trillions of years from now, it might become utterly undetectable to any future observers. This relentless redshifting also explains why the CMB is so cold. Temperature and wavelength are intimately linked. Shorter wavelengths mean hotter, more energetic light, while longer waves are cooler. The CMB's dramatic redshift has effectively siphoned away its heat, leaving it just 2.7 degrees above absolute zero. It's as if the universe took a white-hot brand and plunged it into the deepest cosmic freezer, preserving it as a fossil of its own fiery birth. Yet within that faint microwave hum lies an irony. The more the light redshifts, the clearer its early message becomes. Because this stretching happens uniformly across space, the CMB's patterns remain pristine, undistorted by later cosmic events. It's like slowing down a recording to hear the individual notes more clearly. By studying these redshifted whispers, we're not just observing the past, we're watching the universe itself grow in real time, one stretched wavelength at a time. The cosmic microwave background holds another extraordinary distinction. It's one of the rare cosmic phenomena predicted by theory long before anyone actually observed it. Back in the 1940s, physicist George Gamow and his colleagues Ralph Alpher and Robert Herman were wrestling with a radical idea. What if the universe began as an unimaginably hot, dense fireball? Their calculations suggested that if this Big Bang theory was correct, the universe would have cooled over time, leaving behind a faint afterglow of radiation stretched into microwaves by cosmic expansion. At the time, this prediction seemed almost too audacious to take seriously. The prevailing view among many scientists was the steady-state model, which argued the universe had no beginning and simply existed forever, unchanging. But Gamow's team crunched the numbers anyway. They calculated that this leftover radiation, if it existed, would have cooled to around 5 Kelvin, just 5 degrees above absolute zero. Remarkably, their estimate wasn't far off from the 2.7 Kelvin we measure today. What's astonishing is how few people paid attention. For years, the idea languished in academic papers, a mathematical curiosity rather than a testable hypothesis. Even when other theorists, like Russian astrophysicist Yakov Zeldovich, independently arrived at similar conclusions in the 1960s, the scientific community remained skeptical. The technology to detect such faint microwave signals simply didn't exist yet, or so they thought. Then came the accidental breakthrough. When Penzias and Wilson stumbled upon that mysterious hiss in their radio antenna in 1965, they had no idea they'd found Gamow's predicted relic. It was only after contacting Princeton physicist Robert Dicke, who had independently revived Gamows' idea and was actively building a detector to search for the CMB, that the pieces fell into place. Dicke's team had been beaten to the discovery, but their theoretical groundwork confirmed the universe wasn't just expanding, it had a definite starting point. The beauty of this story lies in its serendipity. Gamow, Alpha, and Herman had theorized the CMB's existence 2 decades earlier, but without precise tools to observe it, their prediction was little more than an elegant hypothesis. Yet when technology finally caught up with theory, the universe handed scientists a gift: the chance to see the past written in microwaves. This interplay between prediction and discovery is what makes science so thrilling. The CMB didn't just confirm the Big Bang, it validated the power of human imagination to uncover truths hidden in the fabric of reality itself. And here's the kicker: Gamow's team didn't just get close with their temperature estimate. Their work also laid the foundation for understanding nucleosynthesis, how the first elements formed in the universe's fiery infancy. So when we marvel at the CMB today, we're not just celebrating a lucky find. We're witnessing the culmination of a bold intellectual journey that began with a few scribbled equations and ended with a Nobel Prize. That's the magic of cosmology. Sometimes the universe whispers its secrets to those daring enough to listen, even decades before the rest of the world hears them. At first glance, the cosmic microwave background appears almost perfectly uniform, a sea of microwaves with temperature variations smaller than 1 part in 100,000. This near-identical glow in every direction seems comforting, like a cosmic blanket woven with incredible precision. But for physicists, this uniformity is actually one of the universe's greatest puzzles, a riddle known as the horizon problem. Here's why it's so baffling. When we look at regions of the CMB separated by vast distances, say, one patch in the northern sky and another in the southern, those areas appear to have the same temperature to within a fraction of a degree. But here's the catch: those regions were so far apart in the early universe that light, traveling at the cosmic speed limit, wouldn't have had enough time to move between them. In other words, these patches were never close enough to exchange heat or information, yet somehow they ended up at nearly identical temperatures. It's like walking into 2 different bakeries on opposite sides of the planet and finding loaves of bread baked to exactly the same temperature, down to the decimal point, without the bakers ever communicating. This paradox led scientists to a radical solution: cosmic inflation. The theory proposes that in the universe's first fraction of a second, space underwent an exponential expansion, inflating faster than the speed of light. Before inflation, all regions we now see as distant were crammed together in a tiny volume, close enough to equalize their temperatures. Then, in an instant, inflation stretched them far apart, preserving that thermal equilibrium like a snapshot. It's as if those bakeries were once a single kitchen, perfectly synchronized before being violently ripped apart, locking their identical conditions in place. Without inflation, the horizon problem threatens to unravel our understanding of the cosmos. The alternative would require some mysterious, faster-than-light mechanism to synchronize temperatures across unreachable distances, a notion that clashes with relativity. Inflation elegantly solves this by giving the early universe a head start, allowing it to homogenize before space itself ballooned. The CMB's isotropy isn't just a curiosity. It's evidence of the universe's most extreme growth spurt, a moment when reality itself outpaced the speed of light. Yet the implications run deeper. If inflation is correct, the universe we observe is just a tiny fraction of what's out there. Regions beyond our cosmic horizon may have undergone different inflationary phases, creating a multiverse of bubble universes with unique properties. The CMB's uniformity, then, is a local phenomenon, a patch of calm in a far vaster and more chaotic cosmic ocean. So when we marvel at the CMB's smoothness, we're not just seeing simplicity. We're glimpsing the aftermath of the universe's most violent and creative moment, a testament to forces so powerful they defy everyday intuition. The horizon problem isn't a flaw in cosmology, it's a doorway inviting us to explore a past more extraordinary than we ever imagined. Hidden within the cosmic microwave background's faint glow lies another layer of secret, subtle swirls and twists in its light that act as a cosmic fingerprint from the universe's earliest moments. This phenomenon, called polarization, occurs when light waves vibrate in a specific direction, like sunlight glinting off the surface of a lake. But the CMB's polarization isn't just random, it carries imprints of the universe's most violent birth pangs, including potential evidence for cosmic inflation. Polarization in the CMB comes in two primary forms, E modes and B modes. E modes, the easier to detect, are curl-free patterns created by density fluctuations in the early universe's plasma, essentially the same ripples that caused temperature variations. But B modes, the curl-like patterns, are far more elusive and exciting. These twisted signatures could be the smoking gun of primordial gravitational waves, ripples in spacetime itself, generated during inflation's exponential expansion. Imagine shaking a bowl of gelatin and watching the ripples freeze in place. That's what inflation's gravitational waves may have done to the fabric of the universe, leaving behind a faint, spiraled signature in the CMB's light. Detecting these B modes is like trying to spot a single snowflake in a blizzard. The signal is incredibly weak, buried under interference from galactic dust and other astrophysical noise. In 2014, the BICEP2 collaboration thought they'd founded a bold claim that made global headlines. But further analysis with data from the Planck satellite revealed the signal was likely contaminated by dust in our own Milky Way. This setback didn't disprove inflation, it simply showed how painstaking the hunt for these primordial whispers can be, yet the scientific payoff would be staggering. Confirming B modes would not only validate inflation, but also reveal the energy scale at which it occurred, a clue to how gravity interacts with quantum mechanics at energies 1 trillion times higher than particle colliders can reach. Different inflation models predict different B mode strengths, so detecting them could help physicists narrow down which version of the theory matches reality. It's like finding a fossilized footprint. The size and depth tell you not just that something passed by, but how heavy it was and how fast it was moving. What makes this search so captivating is the sheer audacity of what we're trying to observe. These polarization patterns, if they exist, were imprinted when the universe was less than 1/trillionth of a second old. The gravitational waves that created them would have arisen from quantum fluctuations, tiny, random jitters in spacetime, stretched to cosmic scales by inflation. It's as if the universe took its faintest whispers and amplified them into echoes that linger for billions of years, waiting for us to decode them. Future experiments like the Simons Observatory and CMB-S4 are being designed with unprecedented sensitivity to tease out these signals from the noise. If successful, they won't just add another piece to the cosmic puzzle, they'll open a whole new window into physics at energies we can never hope to recreate on Earth. The CMB's polarization isn't just a curiosity, it's a time machine, offering us a glimpse into the universe's first moments, when the laws of nature as we know them were being forged in the crucible of creation. The cosmic microwave background doesn't just support the Big Bang theory, it's also a ruthless judge, dismantling alternative ideas about the universe's origins with cold, hard data. Take the steady-state model, once a leading rival to the Big Bang. Proposed in the 1940s by Fred Hoyle and others, this theory argued the universe had no beginning. It simply existed forever, continuously creating matter to maintain a constant density as it expanded. Elegant as it sounded, the CMB obliterated this idea. If the universe had no explosive origin, there'd be no relic radiation uniformly filling space. The steady-state model couldn't explain the CMB's near-perfect blackbody spectrum or its minute temperature variations. flaws so fatal that even Hoyle eventually conceded defeat. But the CMB's role as a cosmic referee goes further. Some theories proposed a cyclical universe where big bangs and big crunches repeat endlessly. Yet the CMB's precise measurements of dark energy revealed by the universe's accelerating expansion suggest space isn't destined to collapse. Instead, it points to a one-way journey toward cold, infinite expansion, leaving cyclical models struggling to adapt. Even more exotic ideas like plasma cosmology or modified gravity theories stumble when confronted with the CMB's intricate patterns. These alternatives often fail to replicate the observed acoustic oscillations, the peaks and troughs, in the CMB's power spectrum that precisely match Big Bang nucleosynthesis predictions. Where things get truly intriguing is with multiverse hypotheses. While the CMB can't directly prove other universes exist, it offers tantalizing hints. Certain anomalies like the infamous cold spot, a strangely large, frigid region in the CMB, have sparked speculation that it could be a bruise from a collision with another bubble universe during inflation. Mainstream cosmology attributes most such quirks to statistical flukes, but their persistence keeps alternative interpretations alive. The CMB also tests string theory's predictions about the universe's topology, whether space is finite and curled into complex shapes. So far, no evidence of such twists has appeared in the CMB's polarization maps, but the search continues. What makes the CMB such a powerful arbiter is its neutrality. Unlike theories built on mathematical elegance alone, the CMB is raw observational data, a fossilized imprint of the early universe that refuses to bend to philosophical preferences. When inflation theory predicted specific patterns in the CMB's fluctuations, and later observations confirmed them, it wasn't just a victory for one idea, it was a demonstration of science's self-correcting nature. The CMB doesn't care about human biases, it simply is whispering truths about reality that we're still learning to translate. This relentless honesty is why cosmologists treasure the CMB. It's not a static monument to the Big Bang's triumph, but a living record that challenges every generation to ask better questions, refine their models, and confront what they don't know. Whether ruling out alternatives or nudging us toward new paradigms, this ancient light remains the gold standard, a beacon guiding us through the fog of cosmic speculation toward the faint, flickering outline of truth. Right now, the cosmic microwave background surrounds us, a faint whisper from the dawn of time, but it won't last forever. The universe's relentless expansion is stretching this ancient light thinner and thinner, redshifting it into ever longer wavelengths. Over trillions of years, the CMB will fade until it becomes indistinguishable from the cold, dark void of space itself. It's a cosmic countdown, one that future civilizations might never even know existed. Think of it like a song playing on an old radio. As the universe expands, it's as if someone keeps turning the dial, shifting the music into lower and lower frequencies until the notes dissolve into static. The CMB started as a blazing chorus of visible light, then dropped to microwaves, and eventually it'll slide into radio waves, then into undetectably long wavelengths beyond our technology's reach. The colder and more stretched it becomes, the harder it'll be to distinguish from the universe's background noise. This fading isn't just a slow dimming, it's an erasure of cosmic history. Distant galaxies are already vanishing from view as their light redshifts beyond detection, but the CMB's disappearance will be far more profound. It's the universe's oldest photograph, and expansion is like pouring bleach over the image pixel by pixel. Future astronomers might look up at a sky devoid of this primordial glow, with no clue that the cosmos once bore the scars of its own birth. What's startling is the timescale. While stars will burn for billions of years, the CMB's detectable signal could vanish in a mere trillion. That might seem like an eternity, but on the cosmic calendar, it's a closing window. Right now, we're living in a privileged sliver of time late enough to have galaxies, planets, and life, but early enough to still catch the fading echo of creation. Civilizations born in the far future won't have that luxury. Yet this inevitable fade out isn't just a loss, it's a clue. The rate at which the CMB dims tells us about dark energy's grip on the universe. If expansion accelerates faster than expected, the CMB could vanish sooner, hinting at forces we've yet to understand. Every measurement we take now is like preserving a page from a book that's slowly burning, ensuring that even as the light fades, its secrets won't be lost to time. The universe forgets, but science remembers. Among the cosmic microwave background's nearly uniform glow, certain anomalies stand out like cosmic thumbprints, none more puzzling than the so-called cold spot, a region of the CMB significantly chillier than its surroundings. Stretching across a patch of sky about 5 times larger than a full moon, this frigid zone is more than just a statistical oddity. It's a mystery that has astronomers debating everything from supervoids to collisions with other universes. One leading explanation suggests the cold spot might be a cosmic void, an enormous bubble of space where matter is unusually sparse. In these vast deserts, photons from the CMB lose energy as they traverse the underdense region, a phenomenon called the integrated Sachs-Wolf effect. Think of it like rolling a marble up a hill. As light exits the void, it must climb out of a gravitational well, sapping its energy and cooling the CMB in that direction. Some studies have indeed identified a sparse region of galaxies aligned with the cold spot, but here's the catch. The void would need to be improbably large, around 1 billion light-years wide, to explain the temperature drop entirely. That's a stretch even for cosmic standards. Then there's the far more speculative theory that the cold spot is a bruise from a collision with another universe during inflation. In this wild scenario, our universe is just one bubble in a frothing multiverse, and the cold spot marks where a neighboring bubble universe nudged ours in the distant past. The idea stems from certain inflationary models, which predict that such collisions could leave localized imprints in the CMB. While the math holds up, the evidence remains circumstantial, leaving most scientists cautious. As one researcher put it, extraordinary claims require extraordinary cold spots, and this one hasn't quite delivered, but the intrigue doesn't stop there. Alternative explanations range from instrumental noise to primordial magnetic fields, or even exotic physics like cosmic textures, hypothetical defects in space-time structure. The cold spot's persistence, though, makes it hard to dismiss. Multiple independent observations, from Planck's all-sky surveys to ground-based telescopes in Chile, have confirmed its existence. It's not a glitch, it's a real cosmic enigma. What makes the cold spot so compelling isn't just its strangeness, it's what it represents. In a universe governed by statistical predictability, anomalies like this force us to question whether we're missing something fundamental. Is it a flaw in our models, a rare statistical fluke, or a window into physics beyond our current understanding? For now, the cold spot remains an open case, a cosmic cold file waiting for the next breakthrough to thaw its secrets. The cosmic microwave background isn't just a relic of the past, it's a cosmic scale, helping scientists weigh the invisible force reshaping our universe, dark energy. Those faint temperature fluctuations we see, they're not random noise. They're a snapshot of the universe's gravitational scaffolding at 380,000 years old, a blueprint that dark energy has been altering ever since. By comparing the CMB's ancient patterns with the distribution of galaxies today, cosmologists can track how dark energy has stretched the cosmos over billions of years. Think of it like a rubber band with markings. Imagine drawing lines on it, then stretching it slowly at first, then suddenly faster. The way those markings spread apart tells you how the stretching force changed over time. The CMB provides the initial markings, the size and spacing of those primordial density fluctuations, while telescopes mapping galaxies reveal how much they've stretched since. The discrepancy between the two is dark energy's signature. Here's where it gets even more precise. The CMB's acoustic peaks, those characteristic hot and cold spots, act as a cosmic ruler. Their angular size on the sky depends on the universe's geometry, which is warped by dark energy's influence. If dark energy is strong, space expands faster, bending light's path more dramatically and making those peaks appear slightly larger. The Planck satellite's measurements nailed this down, revealing a universe where dark energy accounts for 68% of the total energy budget, perfectly matching independent observations from supernova and galaxy surveys. But the CMB doesn't just confirm dark energy's existence, it helps unravel its nature. Is it Einstein's cosmological constant, an unchanging property of space itself? Or something dynamic like a field that evolves over time? The CMB's polarization patterns, especially those elusive B modes, could hold clues. Certain inflationary models predict specific relationships between dark energy and primordial gravitational waves, relationships etched into the CMB's polarized light. What's breathtaking is how this ancient glow bridges cosmic epochs. The same ripples that seeded galaxies also encode how dark energy will shape the universe's fate. Will expansion accelerate forever, tearing galaxies apart, or could dark energy weaken, reversing the process? The answers are hiding in microwaves older than stars, waiting for us to listen. The CMB isn't just a window to the past, it's a mirror reflecting the universe's ultimate destiny. The cosmic microwave background doesn't just tell us what the universe is made of, it reveals something even more fundamental about its very shape. Those intricate patterns we see in the ancient light aren't random splotches, they're cosmic geometry in action, painting a picture of a universe that's astonishingly flat. Not flat like a sheet of paper, but flat in the mathematical sense, a spacetime where parallel lines never meet and light travels in perfectly straight trajectories across cosmic distances. This flatness wasn't a given. According to Einstein's theory of general relativity, the universe could have taken one of three possible shapes: closed like a sphere, open like a saddle, or perfectly flat like an infinite sheet. Each possibility would have bent the CMB's light in distinct ways, leaving telltale signatures in those temperature fluctuations we observe today. A closed universe would have focused light, making hotspots appear larger. An open one would have done the opposite, stretching them smaller. But when scientists measured the angular size of these fluctuations with exquisite precision, they found a perfect Goldilocks scenario: not too big, not too small, but just right for a flat universe. Here's why this matters beyond abstract geometry. A flat universe implies a critical balance between matter, energy, and the expansion rate, what cosmologists call the critical density. Get this, the CMB measurements show the universe's total energy density is within 1% of this perfect balance. It's like balancing a pencil perfectly on its tip for billions of years without it ever falling over. This precision is so uncanny that it became one of the strongest arguments for cosmic inflation. Only a period of exponential expansion could have smoothed spacetime to such perfect flatness. But flatness also decides the universe's ultimate fate. In a closed universe, gravity would eventually win, pulling everything back in a big crunch. An open universe would keep expanding into cold nothingness forever. A flat universe, though, it's a razor's edge scenario. Expansion slows but never stops, with galaxies drifting apart until the last stars flicker out in an unfathomably distant future. The CMB's flatness signature isn't just a geometric curiosity, it's a death certificate for the cosmos, written in microwaves older than starlight. Yet this cosmic flatness holds an even deeper puzzle. For the universe to be this perfectly balanced today, it must have been unimaginably more precise in its infancy, fine-tuned to 1 part in a trillion at 1 second old. Without inflation's smoothing effect, achieving such perfection naturally seems impossible. The CMB doesn't just show us the universe's shape, it's forcing us to ask whether ours is the only possible universe, or just one thread in an infinite cosmic tapestry where other shapes, other fates play out beyond our horizon. So when we say the universe is flat, we're not just describing geometry, we're glimpsing the scaffolding of reality itself, a structure so precisely tuned that its echoes still resonate in microwaves 13 billion years later. And buried in those echoes might be answers to questions we're only beginning to ask about how it all began, where it's headed, and whether our cosmic home is alone in a much vaster multiversal landscape. The cosmic microwave background is more than just ancient light, it's a pristine time capsule, preserving the universe's earliest moments with astonishing fidelity. Imagine stumbling upon a perfectly sealed letter from the distant past, its ink unfaded, its parchment uncrumbled, carrying whispers of a world long gone. That's what the CMB is for cosmologists, a direct line to an era before stars, before galaxies, even before atoms as we know them existed. Every fluctuation, every subtle variation in temperature and polarization is a coded message from the universe's infancy waiting to be deciphered. What makes this cosmic snapshot so extraordinary is its untouched clarity. Unlike starlight, which gets scattered by dust or bent by gravity on its journey through space, the CMB has traveled nearly undisturbed for 13.8 billion years. When we observe it, we're seeing the universe as it was the instant light first broke free, a moment frozen in time, unaffected by the eons of cosmic evolution that followed. It's like uncovering a fossil so perfectly preserved that you can still see the individual cells, the fine details of life exactly as it was millions of years ago. The secrets locked within this glow are staggering. Those tiny temperature variations, they're the imprints of quantum fluctuations, minuscule, random jitters in the fabric of space-time that were inflated to cosmic scales during the universe's first fractions of a second. These microscopic wrinkles became the gravitational seeds for everything we see today, from the smallest dwarf galaxies to the largest superclusters. Without them, the cosmos would have remained a smooth, featureless void, devoid of structure or life. The CMB captures this pivotal moment with such precision that scientists can trace the lineage of galaxies back to their primordial origins, like reading a family tree written in microwaves. But the time capsule's contents go even deeper. The CMB's polarization patterns, those faint swirls of directional light, carry echoes of the universe's first sound waves. In the searing plasma of the early cosmos, matter and radiation were locked in a violent dance, creating pressure waves that rippled outward like thunder after lightning. When light finally escaped during recombination, those waves were frozen in place, their signatures etched into the CMB's polarized glow. By studying these patterns, researchers can reconstruct the universe's acoustic history, listening to the echoes of a cosmic symphony that faded billions of years ago. Perhaps most mind-bending of all, this time capsule is still being decoded. Every advance in technology, from space-based telescopes like Planck to next-generation observatories like the Simons Array, peels back another layer, revealing subtler details, finer patterns, and deeper truths. The CMB isn't just a static relic, it's an active archive yielding new discoveries with every improvement in our ability to read its ancient script. So when we gaze at maps of the cosmic microwave background, we're not just looking at a faded afterglow. We're holding the universe's baby album, flipping through pages written in the language of light, gravity, and time itself. And with each page we decode, we come closer to answering the grandest questions of all: where we came from, what shaped us, and how this vast cosmic story began. The cosmic microwave background didn't always hum quietly in microwave frequencies. It began its existence as a blinding flash of visible light, blazing across the infant universe with the brilliance of thousands of suns. When this light first broke free during recombination, it shone with the intense glow of 3000 Kelvin, radiating in vivid reds, oranges, and yellows similar to the warm hues you'd see in molten metal or the surface of a dim star. But over 13.8 billion years, the relentless expansion of space stretched those light waves like cosmic taffy, transforming what was once a brilliant glow into the faint microwaves we detect today. This transformation is due to a phenomenon called redshift, the stretching of light waves as space itself expands. In the early universe, photons emitted during recombination had wavelengths around 500 nanometers, about the size of a single bacterium, placing them squarely in the visible spectrum. But as the fabric of space stretched, those waves were pulled longer and longer, shifting from visible light to infrared, then to microwaves, and eventually, over trillions of years, into undetectably long radio waves. It's as if the universe took a painting and slowly stretched the canvas, blurring the once vibrant colors into faint, unrecognizable smudges. Redshift isn't just a quirk of the CMB, it's a fundamental signature of our expanding universe. Edwin Hubble first observed it in the light of distant galaxies, noticing their spectral lines shifted toward redder wavelengths as they moved away from us. But the CMB showcases redshift on the most extreme scale imaginable. Its light has been stretched by a factor of about 1,000, meaning every wavelength emitted at recombination is now 1,000 times longer than when it began its journey. This staggering transformation drained the light's energy, cooling it from thousands of degrees to just a whisper above absolute zero. What's fascinating is how this process reveals the universe's expansion history. By measuring precisely how much the CMB has redshifted, cosmologists can calculate how much space has grown since recombination. It's like finding an old rubber band with markings, stretch it out, and the distance between the marks tells you exactly how much force was applied. The CMB's redshift confirms that the universe has expanded by roughly that factor of 1,000 since the era of recombination, a direct testament to the relentless growth of spacetime itself. Yet this ancient light still retains echoes of its brilliant past. Even today, the CMB's spectrum matches that of a perfect blackbody, the telltale signature of thermal radiation, just like the glow from hot metal, only stretched and cooled to microwave wavelengths. That perfect spectral shape is key evidence that this light was indeed once searingly hot, not some modern astrophysical afterthought. It's the same glow, just faded with time, like an old photograph left in the sun. Its colors bleached, but its story still legible to those who know how to look. This relentless redshifting also explains why we can't see the CMB with our eyes anymore. If you looked at the sky 380,000 years after the Big Bang instead of darkness, you'd see a blazing orange-white glow in every direction, like standing inside a scorching oven. Today, that same light is invisible, its wavelengths far too long for human eyes to detect. Only specialized radio telescopes tuned to microwave frequencies can pick up this ancient signal, the last ghostly whisper of a time when the universe was small, hot, and filled with blazing light. Far from being a static relic, the CMB continues to redshift even now. As the universe's expansion accelerates due to dark energy, that faint microwave hum will keep stretching, further dimming into obscurity. Civilizations billions of years in the future may look up at a sky devoid of this cosmic fossil, with no clue that the universe once bore the glowing scars of its birth. We're living in a privileged sliver of time, late enough to have galaxies and planets, but early enough to still catch the fading echo of creation. The CMB's transformation from blazing light to cold microwaves isn't just a curiosity. It's a countdown, a reminder that the universe's history, like all stories, is written in ink that slowly fades. Those subtle temperature variations in the cosmic microwave background aren't just cosmic static, they're the universe's original blueprint, the scaffolding upon which everything we see today was built. When astronomers compare the CMB's faint hot and cold spots with modern galaxy surveys, an extraordinary pattern emerges. Those primordial density fluctuations from 13.8 billion years ago align perfectly with the vast cosmic web of galaxies, clusters, and superclusters stretching across space today. It's as if we've discovered the fingerprints of an ancient architect, revealing how a nearly uniform infant cosmos grew into the structured universe we inhabit. Here's how this cosmic cartography works. Those slightly denser regions in the early universe, the warmer patches in the CMB, acted like gravitational magnets, pulling in surrounding matter over billions of years. Wherever there was a tiny overdensity in the CMB, galaxies eventually sprouted like weeds in fertile soil. The cooler patches, by contrast, became the voids, the empty deserts between galactic cities. Modern galaxy surveys like the Sloan Digital Sky Survey show this in stunning detail. Filaments of galaxies tracing patterns that mirror the CMB's anisotropies with uncanny precision. The largest structures in today's universe, colossal walls of galaxies spanning hundreds of millions of light years, were already encoded in those microscopic ripples from the dawn of time. But the connection runs even deeper. The CMB doesn't just predict where galaxies would form, it reveals the invisible dark matter skeleton holding them together. When light from the CMB travels through the cosmos to reach us, it gets slightly bent by the gravitational pull of massive structures, an effect called weak gravitational lensing. By studying these subtle distortions, scientists can map the distribution of dark matter between us and the CMB, creating three-dimensional charts of the cosmic web's hidden framework. It's like using the CMB as a backlight to silhouette the universe's dark scaffolding, revealing tendrils of dark matter that would otherwise remain invisible. What's truly groundbreaking is how these maps confirm our models of cosmic evolution. Computer simulations that start with the CMB's initial conditions and let gravity work its magic over billions of years produce structures eerily similar to what we observe today. The average distance between galaxy clusters, the branching patterns of cosmic filaments, even the statistical distribution of voids all match predictions born from those ancient microwave fluctuations. It's as if we've found the universe's original recipe, and every ingredient we can measure today, the galaxies, the gas, the dark matter, follows the instructions written in that primordial light. This synergy between the CMB and galaxy surveys is revolutionizing cosmology. By combining data from Planck's CMB maps with projects like the Dark Energy Survey, astronomers are creating the most detailed charts of the cosmos ever made, not just of luminous matter, but of the dark undercurrents shaping everything. These maps don't just show us where things are, they reveal how the universe has grown from a nearly smooth beginning to the intricate cosmic web we see now. Each new survey adds another layer to this grand cartographic project, turning the CMB's whispers from the past into a Rosetta Stone for decoding the universe's structure then and now. The next time you see an image of the cosmic web's glittering filaments, remember, you're looking at the grown-up version of those faint wrinkles in the universe's oldest light. The cosmic microwave background isn't just a relic. It's a litmus test for the boundaries of our understanding, revealing cracks in the foundations of modern physics. One of the most tantalizing mysteries it's uncovered is the so-called Hubble tension, a glaring discrepancy between how fast the universe is expanding today versus predictions based on the CMB's ancient light. According to the CMB's meticulous measurements, the Hubble constant, the rate of cosmic expansion, should be around 67 kilometers per second per megaparsec. Yet when astronomers measure it directly using nearby supernova and pulsating stars, they get a notably higher value, 73. That difference might sound trivial, but in the precision-driven world of cosmology, it's a seismic rift, suggesting something fundamental is missing from our models. This isn't just a minor accounting error. The CMB's expansion rate is derived from the universe's infancy, while modern measurements capture its recent behavior. If they don't align, it implies the rules governing cosmic growth have changed, or that we've overlooked a critical ingredient. Some theorists propose undiscovered dark energy properties, perhaps a force that evolves over time, strengthening as the universe ages. Others speculate about exotic dark matter interactions or even modifications to Einstein's gravity on cosmic scales. The most radical ideas invoke parallel universes or extra dimensions, subtly warping our measurements. What makes the Hubble tension so electrifying is that it's not an isolated anomaly. It's corroborated by multiple independent observations, tightening the noose around the standard model of cosmology. The CMB's role here is pivotal. Its data acts like a cosmic control experiment, a baseline so pristine that any deviation points unambiguously to new physics. Take the clumpiness problem. The CMB suggests matter should be distributed with a certain smoothness, yet galaxy surveys find the universe 10% lumpier than predicted. Add to this quirks like the anomalously large cold spot or unexpected dips in the CMB's power spectrum, and a pattern emerges. A chorus of whispers hinting that our cosmological playbook is incomplete. What's at stake isn't just tweaking a few equations. The CMB's discrepancies could upend our understanding of reality's building blocks. If dark energy isn't constant, as assumed, but dynamic, it might mean the universe's fate isn't a slow freeze but something far stranger, a big rip tearing spacetime apart or a cyclical rebirth. Alternatively, if gravity behaves differently over vast distances, it would rewrite one of physics' most sacred laws. The CMB doesn't just spotlight these puzzles, it offers a way to test solutions. Future observatories like the Vera Rubin telescope will cross-check the CMB's predictions against billions of galaxies, while next-generation CMB experiments hunt for secondary polarization signals that might betray exotic particles or fields. What makes this moment extraordinary is the CMB's dual role as both anchor and compass. It grounds us in the known while pointing insistently toward the unknown, reminding us that the universe's oldest light still has the power to illuminate uncharted realms of physics. Every anomaly, every tension is a breadcrumb trail leading beyond the edges of our current maps, into a cosmic wilderness where the next revolution in understanding might be waiting. Those faint ripples in the cosmic microwave background aren't just random noise. They're the amplified whispers of quantum mechanics, tiny fluctuations from the universe's first moments stretched to cosmic proportions. Imagine the newborn cosmos as a frothing quantum sea, where particles flicker in and out of existence on unimaginably small scales. According to quantum theory, even in perfect vacuum, space isn't truly empty. It crackles with energy, constantly birthing and annihilating virtual particle pairs. In the earliest instance after the Big Bang, these quantum jitters were caught in the rapid expansion of inflation. Their microscopic bumps and dips stretched across light years in less than a blink. What started as fluctuations smaller than an atom became the seeds for galaxy clusters. The mind-bending part, those quantum ripples froze into the fabric of spacetime itself. As inflation ended, the universe's energy converted into matter and radiation, imprinting those quantum patterns onto the searing plasma. When light finally broke free during recombination, it carried this quantum fingerprint, the slight overdensities becoming marginally warmer spots in the CMB, the underdensities appearing cooler. It's as if someone took the static of a quantum field and turned it into the cosmic equivalent of a vinyl record, with grooves deep enough to sculpt galaxies. Here's where quantum weirdness meets cosmic destiny. The CMB's temperature variations measured at just 1 part in 100,000 match precisely what quantum field theory predicts for inflationary expansion. The distribution of hot and cold spots follows a pattern called a Gaussian random field, the statistical hallmark of quantum noise amplified across the universe. Without this quantum origin, the cosmos would lack the initial irregularities needed for gravity to build galaxies. A perfectly smooth universe would have remained forever barren. Modern telescopes reveal this quantum legacy in stunning detail. When scientists analyze the CMB's power spectrum, the mathematical breakdown of those fluctuations, they find peaks and valleys aligning with quantum acoustic waves that rippled through the early plasma. The first peak at around 1 degree on the sky corresponds to the fundamental oscillation wavelength, while subsequent peaks reveal harmonics like notes in a cosmic chord. These patterns don't just confirm quantum effects, they let us measure the universe's composition down to decimal places, since dark matter, ordinary matter, and dark energy each tweak the harmonics in distinct ways. Yet the full implications are still unfolding. Some theories suggest deeper quantum signatures might hide in the CMB's polarization, subtle non-Gaussian patterns or swirling B modes that could reveal quantum gravity effects or even hints of string theory. Others speculate that alternate quantum histories, like loop quantum cosmologies, quantum bounce models, might leave divergent imprints detectable by next-generation instruments. What began as abstract math in quantum textbooks now stares back at us from all sky maps, proving that the largest structures in existence owe their existence to the smallest possible fluctuations. So when you hear that quantum mechanics governs subatomic particles, remember, it also built the cosmic web. Those faint CMB anisotropies are more than just temperature differences. They're quantum mechanics written across the sky, a reminder that the universe's grandest architectures grew from the tiniest tremors in the fabric of reality. And somewhere in those patterns, the answers to even deeper mysteries might still be waiting, new physics hiding in plain sight, encoded in microwaves older than time. Mapping the cosmic microwave background with Earth-based telescopes is like trying to listen to a whisper in a hurricane, possible but overwhelmed by interference. That's why scientists turn to space, launching observatories far above our planet's distorting atmosphere to capture the CMB's faint signals in pristine detail. Two missions in particular transformed our understanding: NASA Wilkinson Microwave Anisotropy Probe, or WMAP, and the European Space Agency's Planck satellite. These orbiting laboratories didn't just take pictures of the ancient light, they decoded its secrets with precision once thought impossible. WMAP, launched in 2001, was the first to map the CMB's temperature fluctuations across the entire sky with razor-sharp clarity. Imagine trying to measure temperature differences smaller than 1/1000th of a degree while floating in the deep freeze of space. WMAP instruments, cooled to just a few degrees above absolute zero, achieved exactly that, revealing the CMB's anisotropies with 10 times the resolution of earlier ground-based efforts. Its data pinpointed the universe's age to within 1%, confirmed the flatness of space-time, and delivered the most accurate census yet of cosmic ingredients: 4% ordinary matter, 23% dark matter, and 73% dark energy. These numbers didn't just refine textbooks, they rewrote them, settling decades of debate about the universe's composition. Yet Planck, launched in 2009, took the game even further. With sensors 100 times more sensitive than WMAP, it produced maps so detailed they revealed the CMB's polarization. The faint directional twist in its light caused by primordial gravitational tugs. Picture trying to detect the imprint of a single snowflake pressed into a glacier. Planck's precision was so extraordinary it could measure temperature variations as minute as 1/1,000,000th of a degree, effectively weighing the universe's dark matter with cosmic-scale balance scales. Its data narrowed the Hubble constant discrepancy, exposed subtle anomalies like the infamous cold spot, and even probed potential signs of other universes in the CMB's statistical quirks. What made these space missions so revolutionary wasn't just their technological prowess, it was their ability to function as time machines. By filtering out modern interference from stars, dust, and even Earth's own microwave emissions, they peeled back 13.8 billion years of cosmic evolution, letting us stare directly at the universe's first light. WMAP and Planck didn't just observe the CMB, they interrogated it, extracting truths about inflation, dark matter's gravitational scaffolding, and the acceleration of cosmic expansion. Future missions, like the proposed Lightbird or CMB-S4, aim to push further hunting for the elusive B-mode polarization that could confirm inflation's quantum origins. But for now, WMAP and Planck stand as twin pillars of modern cosmology, proving that sometimes to understand the universe's beginnings, you need to leave Earth behind entirely. Their data remains a gold mine, with new discoveries still emerging years after their missions ended, testament to the fact that the oldest light in the cosmos still has fresh stories to tell. Among the faint ripples of the cosmic microwave background, some scientists believe there could be footprints from realities beyond our own, ghostly imprints left behind if our universe ever collided with another in the unfathomable chaos of the multiverse. This isn't science fiction, it's a tantalizing possibility born from the CMB's most puzzling anomalies. Take that infamous cold spot, a region of the sky significantly cooler than its surroundings. While most researchers attribute it to a cosmic void or statistical fluke, others wonder, could this be a bruise from a long-ago collision with a neighboring universe? The idea stems from inflationary theory, which suggests our universe is just one bubble in an endless froth of inflating space-time. If other bubble universes exist, their brief intersections with ours during inflation could have left localized scars, subtle distortions in the CMB's temperature or polarization. Picture two soap bubbles bumping in a sink. Where they briefly merge, the surface tension creates a dimple. In cosmic terms, a collision with another universe might have compressed or stretched space-time in that region, leaving behind a telltale cold patch or a swirl in the CMB's polarization patterns. These signatures wouldn't look like random noise. Simulations suggest universe collision imprints would be circular or disc-like, with distinct edges unlike the blurry voids we typically observe. Some models even predict concentric rings of temperature variations, like ripples from a pebble dropped into the cosmic pond. The challenge? These signals would be incredibly faint, buried under layers of galactic dust and later cosmic evolution. It's like trying to spot a single footprint on a beach after a tidal wave has washed over it. Critics argue there's no smoking gun yet. The cold spot's size and temperature could still be explained by rare but natural fluctuations, and no confirmed B-mode polarization from such collisions has been found. But supporters counter that the absence of evidence isn't evidence of absence. We might just need better tools. Future CMB experiments, like the Simons Observatory, will scan with unprecedented sensitivity, hunting for those elusive circular patterns or polarized swirls that could betray a multiversal handshake. What's at stake isn't just the existence of other universes, but the very nature of reality. If the CMB holds proof of a multiverse, it would mean our cosmos is just one page in an infinite library, each with different physical laws and constants. Some might be lifeless voids, others could harbor alien forms of existence beyond our imagination. The CMB then becomes more than a relic. It's a cosmic message in a bottle, whispering that we're not alone in the meta-universe, just impossibly far from our nearest neighbors. Until we decode its deeper secrets, the question lingers: are those faint anomalies in the sky merely cosmic static, or the faint echoes of universes we'll never see? The cosmic microwave background isn't just a relic. It's the universe's ultimate measuring tape, providing a fixed scale against which all cosmic distances can be gauged. Imagine trying to map an endless, ever-expanding landscape with no landmarks or mile markers. That was the challenge cosmologists faced until they realized the CMB's fluctuations could serve as the perfect cosmic ruler, etched into the fabric of space-time itself. This remarkable property stems from the CMB's acoustic peaks, those characteristic hot and cold spots that ripple across its surface like frozen sound waves. During the universe's first few 100,000 years, matter and radiation were locked in a violent dance, creating pressure waves that traveled through the searing plasma at nearly 2/3 the speed of light. When the universe cooled enough for atoms to form, these waves froze in place, imprinting their signature on the CMB. the distance these sound waves could travel before recombination, about 500,000 light-years, became the fundamental yardstick of cosmology, known as the sound horizon. Here's the brilliant part: because we know exactly how large these frozen waves should appear based on the universe's geometry, we can use them to measure cosmic distances with extraordinary precision. It's like having a standard ruler placed at the edge of the observable universe. By measuring how big it looks from Earth, we can calculate the distance to that point. When we observe these acoustic peaks in the CMB, appearing about 1 degree apart on the sky, that angular size tells us the universe is geometrically flat to within 1% accuracy. Any curvature, positive like a sphere or negative like a saddle, would make these peaks appear larger or smaller than predicted. This cosmic ruler has revolutionized distance measurements across the universe. When astronomers study baryon acoustic oscillations, the faint echo of those primordial sound waves preserved in galaxy distributions from billions of years later, they're using the same standard ruler imprinted in the CMB. By comparing how the ruler's apparent size changes at different cosmic epochs, scientists can track the universe's expansion history with unprecedented accuracy, testing theories about dark energy and cosmological models. What makes this even more powerful is how it connects vastly different eras. The same sound waves that left their imprint in the CMB also seeded the large-scale structure we see today. Galaxy clusters tend to be separated by the same 500 million light-year scale, a direct inheritance from those primordial oscillations. The CMB ruler thus bridges timescales from the universe's infancy to the present, letting us measure cosmic growth across nearly 14 billion years with a single, consistent benchmark. Future surveys will push this technique even further, using millions of galaxies as tracers to map the universe's expansion in 3 dimensions. But none of this would be possible without that original, perfect imprint, the CMB's frozen sound waves serving as astronomy's most reliable yardstick, a ruler carved into the sky when the universe first became transparent and still guiding our measurements today. Hidden within the cosmic microwave background's intricate patterns lies an unexpected revelation: the fingerprints of the universe's most elusive particles, neutrinos. These ghostly subatomic particles, so light they barely interact with matter, have left subtle but measurable imprints on the CMB that allow scientists to weigh them and trace their cosmic influence. It's like finding shadows cast by invisible dancers. The way these particles altered the early universe's density fluctuations reveals secrets about their mass and behavior that laboratory experiments struggle to pin down. During the universe's first few seconds, neutrinos roamed freely at nearly the speed of light, their sheer numbers making them a dominant force in the cosmic plasma. As they streamed out from hot regions into cooler ones, they carried energy away, smoothing out some of the infant universe's density variations. This neutrino drag left a distinct signature in the CMB's temperature fluctuations, a suppression of small-scale hot and cold spots that wouldn't exist if neutrinos were massless. The effect is subtle, akin to noticing the faintest ripple in a pond has a slightly different shape because a single drop of rain fell elsewhere, but measurable with precise enough instruments. The Planck satellite's data allowed cosmologists to perform cosmic-scale neutrino weigh-ins. By analyzing how much the CMB's small-scale fluctuations are dampened compared to larger ones, researchers determined that the combined mass of all 3 known neutrino types can't exceed about 0.12 electron volts. That's over 500,000 times lighter than an electron. This might seem negligible, but in the particle physics world, it's groundbreaking. Before the CMB measurements, we only knew neutrinos had mass from observations of their oscillations between types. The cosmic microwave background gave us the first cosmological upper limit on how much. What makes this even more fascinating is how the CMB constraints complement Earth-based neutrino experiments. Underground detectors like Super Kamiok and measure neutrino mass differences, while the CMB provides the absolute scale when combined with galaxy surveys. Together, they paint a picture of neutrinos as cosmic sculptors, particles so light they barely bend space-time, yet numerous enough to influence how galaxies cluster over billions of years. The CMB shows that while these particles account for less than 1% of the universe's total mass energy, their early universe behavior left an indelible mark on the cosmic web structure. Future CMB experiments promise even sharper neutrino insights. Projects like CMB S4 aim to detect how neutrinos slightly warp the CMB's polarization through gravitational lensing, an effect that could reveal whether neutrinos behave differently in the early universe's extreme conditions than in today's particle accelerators. Some theories even suggest primordial neutrinos might have interacted with dark matter, leaving exotic polarization patterns that could rewrite our understanding of both particle families. So when we study the CMB's faint anisotropies, we're not just mapping the past, we're conducting particle physics on a cosmological scale. Those barely their temperature variations encode data about particles so elusive that trillions pass through your body every second without a trace. The universe's oldest light has become an unlikely microscope, revealing secrets about the tiniest residents of the quantum world. The cosmic microwave background might hold clues to one of physics' most speculative mysteries, whether our universe has hidden dimensions beyond the familiar three of space and one of time. While mainstream cosmology treats the CMB as a four-dimensional relic, some theorists propose that subtle anomalies in its patterns could betray the presence of extra-spatial dimensions, curled up so tightly that only their faintest gravitational whispers remain. These ideas remain controversial, but they offer a tantalizing possibility that the universe's oldest light could illuminate realms beyond our everyday perception. Take the cold spot, for instance. This unusually frigid region in the CMB spans nearly 1.8 billion light-years, far larger than standard inflation models predict. While most explanations involve cosmic voids or statistical flukes, a handful of physicists suggest it might be a shadow cast by higher dimensional structures intersecting our universe. In some brainworld scenarios where our three-dimensional universe floats within a higher dimensional bulk, collisions with other branes could transfer energy asymmetrically, leaving imprints like temperature dips in the CMB. It's as if we're seeing the cosmic equivalent of a finger pressing into the fabric of our reality from outside. Even the CMB's overall statistical oddities, like unexpected alignments of large-scale fluctuations dubbed the axis of evil, have prompted speculative links to higher dimensions. Certain string theory models predict that compactified extra dimensions, think 6 or 7 spatial dimensions curled into microscopic loops, could subtly alter gravity's behavior on cosmic scales. These modifications might twist the CMB's polarization patterns in ways that deviate from standard inflationary predictions, creating anomalies that future telescopes could detect. Imagine trying to visualize a hypercube by studying its three-dimensional shadow. The CMB might be our shadow of a more complex, multidimensional reality. Critics argue these ideas stretch Occam's razor to its limits. Most CMB anomalies have plausible explanations within standard cosmology, and invoking extra dimensions risks becoming a theory of anything that's impossible to falsify. Yet proponents counter that science progresses by exploring outliers. After all, quantum mechanics and relativity once seemed equally outlandish. Next-generation CMB experiments like CMB S4 could settle the debate by hunting for exotic polarization signatures or non-Gaussian patterns that higher dimensional physics might produce. What makes this approach so compelling is its inversion of scale. Extra dimensions, if they exist, are thought to be smaller than an atom, yet their cosmological effects might be writ large across the entire sky. The CMB becomes a bridge between the quantum and cosmic, a canvas where the universe's smallest secrets paint its grandest structures. Whether these theories hold up or not, they remind us that the cosmos' oldest light still has the power to illuminate not just where we've been, but what lies beyond the edges of our current understanding. The cosmic microwave background isn't just a scientific marvel, it's a muse, inspiring artists, musicians, and thinkers to reinterpret its ethereal beauty through their own creative lenses. Take the iconic CMB map with its swirling blues and reds depicting temperature variations across the sky. What scientists see as data points, artists like Leo Valerial transform into breathtaking installations. His cosmic microwave horizon at New York's Hayden Planetarium projects the CMB's patterns across a domed ceiling, turning quantum fluctuations into a pulsating light show that immerses viewers in the universe's birth. It's science as spectacle where the Big Bang's afterglow becomes a living canvas. Musicians, too, have found rhythm in the cosmos. Composer John Luther Adams translated the CMB's temperature data into sound for his orchestral work Become Ocean. By assigning musical notes to different temperature values, he created a haunting melody from the universe's oldest light, literally letting the cosmos sing its own history. Electronic artists like Brian Eno have sampled the CMB's static into ambient tracks, weaving its white noise into soundscapes that feel both ancient and eerily futuristic. These works don't just borrow from science, they reimagine it, inviting audiences to feel the universe's scale in ways equations alone can't convey. Philosophers and writers, meanwhile, grapple with the CMB's existential weight. Its pervasive glow, light older than stars, has become a metaphor for humanity's search for meaning. In The Order of Time, physicist Carlo Rovelli describes the CMB as the faint memory of a vanished world, a reminder that everything we know emerged from chaos. Novelists like Kim Stanley Robinson weave it into sci-fi plots, using its anomalies as gateways to alternate realities in books like 2312. Even spiritual leaders cite its uniformity as a symbol of cosmic unity. The Dalai Lama once likened the CMB's interconnectedness to Buddhist concepts of oneness. Perhaps most strikingly, the CMB has birthed an entire genre of data art. Projects like CMB by artist Rafik Anadol use machine learning to animate Planck satellite data, transforming the universe's infancy into a dynamic, ever-evolving digital mural. Schools from Tokyo to Berlin host exhibitions where students reinterpret CMB maps through sculpture, textiles, or virtual reality, proving science and creativity aren't opposites but collaborators. What makes this cultural resonance so powerful is its universality. The CMB isn't locked away in labs, it's a shared inheritance, a story written across the sky that belongs to poets and physicists alike. Whether through a symphony's crescendo or a painter's brushstroke, humanity keeps finding new ways to honor the light that began all light, proof that discovery and wonder are, at their core, deeply human pursuits. The cosmic microwave background isn't just a relic we've studied, it's a frontier we're still actively exploring, with next-generation missions poised to extract even deeper secrets from this ancient light. Leading the charge is CMB S4, an ambitious international project that will deploy a network of ultra-sensitive telescopes across Chile and Antarctica, creating the most detailed maps of the CMB ever attempted. With detectors 20 times more sensitive than Planck's, this megaproject aims to measure the CMB's polarization with such precision that it could finally detect primordial gravitational waves, those elusive ripples in spacetime predicted by cosmic inflation. Imagine trying to photograph a snowflake from 10 miles away, then suddenly upgrading to a microscope that reveals the crystalline structure of each individual ice branch. That's the leap in resolution CMB S4 promises. But why stop at better maps? The Simons Observatory, already under construction in Chile's Atacama Desert, will act as a pathfinder for CMB S4 with tighter focus on B-mode polarization. Its small aperture telescopes will scan large swaths of sky to hunt for inflationary gravitational waves, while large aperture instruments will zoom in on galaxy clusters, warping the CMB through gravitational lensing. This two-pronged approach could settle long-standing debates: is dark energy truly constant, or does it evolve over time? The answer might lie in subtle distortions of the CMB's polarization that only these next-gen detectors can spot. Meanwhile, space-based projects aren't bowing out. Lightbird, a Japanese-led satellite mission slated for launch in the late 2020s, will survey the entire sky in 15 frequency bands, filtering out galactic interference with surgical precision. Free from Earth's atmosphere, which subtly distorts microwave signals, it could achieve sensitivity to primordial B modes 100 times better than Planck. Think of it as putting noise-canceling headphones on the universe, isolating the CMB's faintest whispers from the cosmic static. What makes this new wave of experiments revolutionary isn't just their technical specs, it's their potential to answer existential questions. Some theories suggest the CMB might contain evidence of cosmic strings, hypothetical defects in space-time left over from the universe's fiery birth. Others speculate these missions could detect anomalies hinting at entirely new physics, like actions or other dark matter candidates interacting with the early plasma. There's even a chance we'll find evidence for non-Gaussian patterns in the CMB's fluctuations, deviations from the standard statistical model that could point to exotic early universe phenomena. The stakes couldn't be higher. If inflation's gravitational waves are detected, we'll have direct evidence for quantum gravity at energy scales 1 trillion times beyond particle colliders. If not, it could force a radical rethink of cosmic beginnings. Either way, the CMB remains our clearest window into physics at energies we can never recreate on Earth, a natural laboratory written across the sky. As these missions come online over the next decade, they won't just add to our knowledge, they might redefine what we thought was possible, proving once again that the universe's oldest light still has the power to illuminate its deepest mysteries. The cosmic microwave background does something extraordinary. It transforms the vast, impersonal universe into a story we're part of, a narrative that began long before us and will continue long after. When we study this ancient light, we're not just observing distant physics, we're retracing our cosmic genealogy, connecting the dots between the quantum flickers of the Big Bang and the fact that we're here at all, able to ponder it. Every photon in the CMB has traveled 13.8 billion years to reach us, carrying a message from an era when the entire cosmos could fit into a volume smaller than a grapefruit. And now, those photons land in telescopes built by curious creatures who evolved from stardust, completing a loop as poetic as it is scientific. What's remarkable is how this connection bridges scales. The same quantum fluctuations that seeded galaxies also set the stage for Earth's formation, and ultimately, life. Those subtle wrinkles in the CMB weren't just abstract patterns. They were the gravitational seeds for the Milky Way, the solar system, and the planet under our feet. In a very real sense, the imperfections in this primordial light sculpted the conditions that allowed atoms to assemble into DNA, neurons, and the human mind's now decoding those signals. It's as if the universe left itself a breadcrumb trail, and we've followed it backward to our own origins. This relationship isn't passive. By interpreting the CMB, we've become active participants in the universe's self-understanding. The cosmos birthed conscious beings capable of studying it, not just as outsiders but as products of its own physical laws. When satellites like Planck map the CMB's polarization, or when theorists unravel its implications for dark energy, we're witnessing the universe examining its own reflection through us. The Chilean poet Pablo Neruda once wrote, "We are made of star stuff, but the CMB takes this further. We're not just made of stars, we're the universe's way of comprehending its own first light." There's humility in this, too. The CMB reminds us that humanity occupies a sliver of cosmic time, late enough to evolve intelligence, but early enough to still catch the fading echo of creation. Civilizations billions of years from now may gaze at a sky where the CMB has redshifted into oblivion with no trace of the universe's fiery birth. We're privileged to live in an era when this ancient glow remains visible, offering clues to questions our ancestors could only pose as myths. Yet the CMB's greatest gift might be perspective. In a world often divided by borders and ideologies, it offers a unifying vision, a reminder that every human, every creature, every atom on Earth shares the same cosmic ancestry, forged in the same primordial glow. Those microwaves bathing the night sky don't discriminate. They fall equally on deserts and cities, forests and oceans, connecting all of us to something vaster than our planet's petty conflicts. The CMB doesn't just illuminate the past, it invites us to see ourselves as temporary but exquisite participants in an epic that began with a flash of light and will continue long after our chapter closes. So the next time you hear about the cosmic microwave background, don't just think of it as data points on a graph. It's the universe's origin story and ours, written in a language of heat and light that we've somehow learned to read. And in that reading, we've found something unexpected, not just how the cosmos began, but how deeply we belong to it. From its accidental discovery as radiostatic in 1965 to its current role as cosmology's most trusted roadmap, the cosmic microwave background has rewritten our understanding of reality. Over these 30 mind-blowing facts, we've traveled back to the universe's infancy, 380,000 years after the Big Bang, when light first broke free from a searing plasma fog. We've decoded how its near-perfect uniformity hides quantum wrinkles stretched to cosmic scales, how its faint cold spots might whisper of multiversal collisions, and how its precise temperature variations reveal dark energies accelerating grip on spacetime. This ancient glow isn't just radiation, it's a time capsule preserving the universe's raw ingredients, 5% atoms, 27% dark matter, and 68% dark energy, a recipe no lab could have imagined. The CMB's revelations keep unfolding. It confirmed inflation's exponential expansion, weighed ghostly neutrinos through their gravitational shadows, and even hinted at higher dimensions through statistical anomalies. Its acoustic peaks serve as a cosmic ruler, measuring dark energy's push across billions of years, while its polarization patterns could still betray primordial gravitational waves, the smoking gun of quantum gravity. Every mission from Coldest to Planck has peeled back another layer, turning what was once dismissed as mere static into the Rosetta Stone of cosmic evolution. Yet for all we've learned, the CMB's greatest gift might be its unanswered questions. Why does the Hubble constant disagree with local measurements? Is the cold spot a statistical fluke or a window into other universes? Could future telescopes detect the imprint of cosmic strings in its polarized light? This glow connects us to the past but also points to the future, to discoveries waiting in upgraded detectors like CMB S4, which will scan the sky with 20 times Planck's sensitivity. As the universe expands, this ancient light is fading, redshifting into obscurity over trillions of years. We're living in a privileged moment, late enough to decipher the cosmos' origins, but early enough to still catch its first light. So the next time you stare at static on an old TV, remember, you're glimpsing the same electromagnetic whisper that birthed galaxies. The cosmic microwave background isn't just a fossil, it's an invitation. An invitation to keep exploring, to question anomalies, and to wonder what other secrets this 13.8 billion-year-old messenger might still hold. If these revelations lit up your curiosity, imagine what's left to discover. Hit subscribe and let's keep decoding the universe together, one photon at a time.